Driving IP and Optical Benefits with Multi-Layer Integration, sponsored by ECI. Before we begin, I wanted to cover a few housekeeping items. On the right-hand side of your screen is the Q&A. If you have any questions during the webcast, you can type your question into the Q&A box and submit your questions to our speakers. All questions will be saved, so if we don't get to answer you, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow Help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the green Resource List widget. Towards the end of today's presentation, we'll ask you for your feedback. A survey will pop open on your screen and will only take 1 minute to complete. Your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to return the event over to Heavy Reading's Principal Analyst, Sterling Perry.
Thank you, Rebecca. Hi, and welcome everyone to Driving IP and Optical Benefits with Multi-Layer Integration, sponsored today by ECI. We've got a great webinar planned for you today. Happy to have Scott Wilkinson. He's Senior Director of Portfolio Marketing with ECI, frequent speaker at Heavy Reading, Light Reading events. Hi, Scott. Welcome back to Light Reading.
Thanks, Sterling. Glad to be here.
Great. Looking forward to what you have to present. So everyone should see the agenda here in front of you. I'll give a introduction to IP and optical integration. This is a very hot topic right now, and there's still some confusion on it, so I'll explain out some things, talk about the drivers, and then I'll hand things over to Scott, who will cover a look at the flexible photonic layer, what that means, and the different enablers for that. And then a future of IP over DWDM, so ECI's views on where this trend is going, and then Q&A at the end. We should have about 10 to 15 minutes for that, as we typically do. So please do ask those questions as they come to you. We'll gather them up, and we should get to quite a few of them at the end. We've also got 2 poll questions, one after my introduction and then another one at the end. So interested in your feedback for those as well. So let's get into the introduction. So in terms of IP and optical integration, there's actually quite a few terms that are used, which does cause some of the confusion. IP and optical integration, IP over DWDM, IP over glass, IP plus optical synergy. These are all used to describe basically IP and optical integration, and they are often used interchangeably. Sometimes different companies use them to try to distinguish different types, but looking through, as Scott and I have worked on this project, there's not actually a lot of consistency with that. So they are essentially could mean all the same thing. Basically, there's 2 types of integration, regardless of how it's termed, and they're shown here on this slide: physical integration and then control and management integration. Physical integration referring to one hardware network element that's integrating the IP and the optical layers together. And then the control and management integration, which involves physically separate network elements, but the integration is a software integration via the control and management planes. On the left of this slide is a depiction of physical integration. And so in this, we've got long-reach DWDM optics that are placed directly into the router in place of the short-reach client optics that would normally fit on the router. So you swap out the client optic, you put in a longer-reach DWDM optic. And this approach eliminates the back-to-back transponders that are otherwise needed to connect a router to a DWDM system. Normally there's a router sitting next to DWDM, and they have to connect with short-reach, and then it goes out DWDM. So it's a CapEx savings play. Historically, it's been around as a concept for quite some time. On the right, I show the control and management plane integration. So here, the router and the DWDM systems are physically separate elements, but the management and control is via a unified software layer. And so this is where SDN comes into play as we talk about the moving forward types of architectures, the next-gen architectures are SDN. Historically, though, pre-SDN and pre-open APIs, what this type of integration typically meant is that you had a single vendor who owned a router, who built routers, built DWDM systems, and they would manage those together through the network management system, but it was single vendor. So that's the two types of architectures. IP and optical integration as a concept has been around for quite some time, decades really, and I've been showing this slide lately as a way to talk through why it's existed so long and why we're looking at this trend as in a new light going forward. So as we know, it's been around since 2000, probably even a few years earlier in some of the very technical conferences, but despite all that activity, we never really got to wide commercial adoption. It was always a bit of a niche play. And there were we've worked out four main barriers to why it never really took off in wide-scale adoption. Those are listed on the left there. But a risk of vendor lock-in, faceplate and capacity trade-offs, lack of a flexible photonic layer, and then finally the lack of a demonstrable business case for IP and optical integration, regardless of the architecture. So I'll go through these briefly here. Some are related to the physical integration challenge. Some are deal with hardware immaturity, and some of them have to do with the software element and the advent of SDN and software programmability. The vendor lock-in issue was twofold. The physical integration model, as I showed on that last slide, typically that was a single vendor implementation for many reasons, technical as well as kind of go-to-market and strategy. And so a lot of operators were not willing to have a single vendor at both those layers. But even the control and management, as I also described on that last slide, historically due to complexity and a lot of other things, that was also a single vendor implementation. Going forward, looking at SDN and looking at open APIs, we're coming to a much more open approach to IP and optical, which brings in multi-vendor, so multi-layer, multi-vendor. And it's changing things quite a bit in terms of operator interest. The faceplate and capacity trade-off issue was relates to the physical integration. Historically, if you look at the leading edge long-reach optics, they were tend to be twice as large as the client optics of the same rate. So what would happen is you swap out that client optic and put in a long-reach optic, you were sacrificing up to half the capacity of that router, which operators were not willing to do to save on the capex of eliminating those back-to-back transponders. Scott will talk quite a bit about the flexible photonic layer. This was something that was needed as a technical evolution to the optical layers. A flexible photonic layer with colorless and directionless ROADMs meant that you could really switch the photonic layer in an automated way via software with these hardware advances, and it made the case for integrating the two IP and optical layers together much more compelling, which also relates to that last one. Once we've got this new approach that's control and management focused, once we have open standards, once we have a flexible photonic layer, operators are able to make a business case for moving to IP and optical much more than they have in the past. And this is why we think we're moving into a new era of IP and optical, and one that will lead to wide-scale commercial adoption, as both Scott and I will talk through as we go through the hour. The last three slides I have are from a network operator survey that we conducted. We published in June of 2016. We had 86 network operators responding globally to this one. And the reason I'm showing these slides is to show that this IP and optical integration trend is not something that's vendor push, as it had been often in the past, but is really something that the network operators are asking of their vendors and as something that they see as absolutely required for their network architectures moving forward. So the first question shown here, we'd ask, what's the most important business benefit that carrier SDN offers to your company? And this is fairly consistent. We've asked this type of question in different surveys. And really coming to the front here is this ability to create and deploy services more rapidly, 43%. This is really the primary driver that network operators see in moving to SDN and what it can do for the network. Second to that was the OpEx savings benefits of an automated network and reducing the amount of human touch on the network. And then third, though it's fairly far behind, was the pure CapEx savings arguments. Getting into IP and optical issues specifically, we had a couple questions in the survey that were on this topic. This one here, we asked, where does your company expect to see the biggest benefits from network optimization over the next 3 years? So optimizing the network, running the network more efficiently, much more efficient use of the capacity and the equipment that's in your network. And the place where network operators see that as most valuable is multi-layer optimization across both IP and optical. So 57% saying that's the primary benefit of network optimization. So very clear benefit of IP and optical shown right there. And then the final one to really illustrate the point of IP and optical being an operator-driven trend this time around, we asked to rate the importance of a number of carrier SDN use cases for their companies over the next 2 to 3 year timeline, and we gave them a number of options. I circled 4 of them here. So these are arranged in terms of the highest priority, so which ones got the greatest response rate for high priority. Number 3 on the list, 51%, specifically multi-layer optimization, IP and optical integration as being critical SDN use case. And even if you look at any of these ones that are circled there, and all of them, 49% and higher, saying critical. All of them, you can make a case for IP and optical integration as either a critical enabler for that use case or something that when you integrate those 2 layers together, it makes that use case much more compelling for any of these: provisioning, monitoring, management, planning, bandwidth on demand, and of course, the multi-layer integration that I cited. The other point I'll make on this, which was also consistent with past surveys we've done for operators, is the pure optical use cases that don't involve any type of integration with IP actually end up down the bottom of the list in terms of use cases. Several years ago, it became very clear to us at Heavy Reading that the SDN and optics by itself is not very compelling, but it really was to really hook that optics into the IP layer and get benefits much greater than what you could do with either the optics alone or SDN at the IP layer alone, and that's clearly shown through in multiple surveys, including this most recent one. So with that introduction, I'm going to hand things off to Scott momentarily, but before we get there, I want to get to our first poll question. And so we've got, and this is an interesting one. Scott and I were just chatting before the webinar started. We've never asked this question before, so I'm quite curious what will come of it. It should be up in front of you right now. And so we're asking, for which applications should colored DWDM optics be placed directly into routers? So looking at that physical integration trend of optics onto the router, which type of application is it most useful for? So we've defined out 3 of these. Short haul, which we've defined as less than 80 kilometers. Mid-haul, which we've defined as running from about 80 kilometers to 200 kilometers. And then long haul, for the case of this question, we've specified as 200 kilometers or greater distances. So that's long haul in this context. If you think IP optics directly physical integration is needed for all of them, hit all of the above. If you're not a big fan of this direct integration, then you'd click none. And we'll see. I want to give a moment. We have quite a few people on, so I want to give a moment to get to critical mass. But, yeah, this was sort of inspired. Again, Scott and I were chatting as we worked on the project. The Inphi Microsoft announcement from last year at OFC caused quite a bit of commotion as really an application for putting the optics directly onto the switching and routing equipment. So it's kind of rekindled this trend. I'll give it a moment. Scott, any guesses on what you think will come back before I hit the button? We can push him out to put you on the spot.
Well, like you said, I think based on Microsoft and Inphi, short haul is probably the one that's gotten the most notice recently. Obviously, there are other carriers who have been very opposed to doing it at any point. And then there are, you never know, every once in a while you'll see some announcements in the other range. So my guess is you'll see a response in the short haul. And
all right, let's see. We've got
that's the reason we're asking the question, right?
Yeah, let's see. Here we go. So interesting, always interesting to come out. So you're right, of the single variants, the short haul did come out the most, 23% there. A lot of people saying all of the above, about a third of the audience saying all of them. And then let me just give one more push to see if it moves. Yeah, so about 18% saying there's no interest. So still, and this has been over the decades, there is interest in this physical integration application. I don't know, any additional thoughts? All of the above was the winner in this case, but as you said, the short haul, quite a bit of interest. You'll talk through things quite a bit, but yeah.
Yeah, it's interesting. It'd be interesting to try to parse that in different ways, say if it's short haul and medium haul or short haul and long haul, how that would actually fall out. I think what's interesting there is that 18% of people saying even in the short haul, you would never integrate them. So that's
right.
That's not. I did not expect that number to be that high. That's interesting.
Okay, good. And then that long haul one with very little interest, of course, that relates to that historical faceplate trade-off that I talked about, I believe, is why there'd be less interest there. But good, always good stuff. Let me do one more push of that just to make sure, because I think we'll use this data ourselves going forward. Looks great. So let's move on. Yeah, so Scott, I'll bring you in, and you want to talk through the flexible photonic layer, so I'll let you take it from here.
Sure. So looking through the attendees list, there's a good chance that some of this is going to be review, at least at the front for some of you. But for others, this will be new information. So bear with me if you've seen it before. If you haven't seen it before, hopefully this is useful. I thought the first thing we really should do is define what is the flexible photonic layer compared to what we would call traditional optical networks. A traditional optical network would be the WDM point-to-point, perhaps with SONET SDH protection. Generally, as Sterling was talking about, external management, performance monitoring, everything is done through some overlayer that looks down on everything. And what we're moving towards is the flexible optical network that I'll talk a little bit more about, where dynamic WDM is in there. You got protection of the WDM layer. If you're doing sub-wavelength management, generally that's moving to OTN as opposed to something like SONET SDH. And the elements themselves have become smart. Network is more automated. Provisioning, maintenance, those kind of things are all built into the network elements themselves. And so these are the things that I'm going to talk about in the next couple of slides to define what we meant by the flexible photonic layer, because that defines how this IP optical integration is moving forward. Now that we have a flexible photonic layer, we can do so much more with IP and optical than we could ever do in the past. And the first change, of course, is the transponders themselves. A traditional transponder was just a one-for-one, turning from gray into a WDM. Whatever protocol came in was the protocol that came out. You bought a specific transponder for a specific application. You plugged it in, and it did what it was supposed to. These days, transponders do so much more. They're software tunable for high-speed optics as well as low-speed optics. You can use one transponder for all sorts of different wavelengths and speeds and rates and signals. They've got a lot of other capabilities built into them. The picture off to the right is encryption, which you can now buy in a transponder. Single transponder per card is no longer something that you see. A transponder card now has multiple transponders. And inside that, these days, you can see things like cross connects. So a single interface can go to multiple outputs. It can be protected. You can do unprotected. You can do multicast. You can do one for one, one for N, all built onto the same transponder. So what we used to think of as a transponder these days, it's hard to call it just a transponder because the cards themselves, the hardware themselves, is so much more complex and capable than it ever was in the past. And that's been sort of the first step towards a flexible photonic layer, is getting those transponders to do more than they were before. The one that people may be more familiar with is the next one, which is the flexible optics themselves. In the past, the first transponder optics, the first WDM optics, you bought a specific optic. You can still buy these, by the way. Single wavelength, single protocol, certain modulation scheme, typically on-off keyed. It went over a certain distance. You bought them based on what distance and what wavelength you needed, and all that has changed. I think the first change was probably the software tunable over the entire C-band. For those of you who've been in the business long enough, you remember the first tunable ones were over a specific part of the C-band, maybe over a certain number of wavelengths. It only became a little bit later that we were able to do the whole C-band, and now we can do the extended C-band with the same optics. And again, for those of you who come in relatively recently, this seems like just a rational, normal thing. Why wouldn't you do this all along? For those of us who've been in it for a while, this is still really, really cool. That you buy one small pluggable optic, and through a software command, you can make it act like lots and lots of optics, up to 88, 96, whatever you want it to be. And that, of course, has completely revolutionized the way that we do WDM. In terms of sparing and performance and operations, everything has changed because of that. Changing the fixed rate and protocol was another big step. You no longer bought a single optics to do your TDM and another one to do your fiber channel and another one to do your SAN or WAN. These days, they can do a wide variety, which makes sense. Just a matter of changing some of the components inside to be more flexible than they used to be. And they're all software programmable and protocol programmable. That, again, is another big deal for those of us who've been in it for a while, that you don't have to decide beforehand what it's going to be for the rest of its life. You don't have to have multiple spares around. You can do all this very, very flexibly. But the most interesting one recently is this change in the modulation scheme. Up to 10 gig, and even some ways up to 40 gig, the only way you sent signals over a fiber optic line was by turning the laser on and off really, really fast. On-off keyed. It was on or it was off. It was a 1 or a 0. When we got beyond 10 gig, some of the impairments started to cause problems, and people started looking for other ways to do things beyond 10 gig. And that's where we came up with multiple layers, multiple levels and multiple phases, things like QPSK and QAM. Don't worry so much about what the acronyms mean. What it really says is we've taken a protocol set that was originally designed for things like satellite transmission over noisy environments, and we've adapted those to fiber, which was never a noisy environment until we got to really high speeds. Now we're able to pack a lot of information into a small amount of spectrum and send it over long distance just like the satellite guys used to. But we're able to do it a lot better because we have that fiber medium. Now that we're able to do that, a lot of that is very much programmable. What kind of protocol you use, 16 QAM versus QPSK, can be programmed into the hardware itself. So you can do, like shown in the diagram here, you can go over 400 gigabits per second over 800 kilometers, and with the same hardware, go 4,000 kilometers at 200 gig without changing anything else. And you might say, well, why does that actually matter? And it only matters in a couple of cases, but those are very important cases. One is a programmable network. If you have, for example, traffic that's going over a relatively short link and that link breaks and you have to switch to a protection link, and the protection link is longer, it's always preferable to cut the bandwidth down a little bit and keep the link up as opposed to losing the link altogether. The other application, of course, is not knowing exactly where things are going to go. As you move WDM around, it becomes more dynamic. It may change. And then, of course, there's always the idea of having a single set of hardware to do multiple applications, which keeps the cost down. This has become a huge deal in a flexible photonic layer. A lot of the limitations that were always put forward for photonic layers goes away when you start to do these kind of things. And of course, we're just at the beginning of this. Adding different kinds of modulation schemes and other things in there is going to take us to 200 gig to 400 gig to terabit and beyond. So it's very, very interesting stuff. And then there's the WDM layer itself. And it's a bit of a spaghetti in the picture there. If you can imagine those moving around over time, in the past, we had, for WDM, fixed add drop. If you look at some of the early IP over WDM papers and discussions and articles, they were always talking about the switching happening outside of the WDM and the WDM just being a big virtual fiber pipe between two locations. And that was one of the reasons at the beginning of IP over WDM discussions, people said it didn't make a lot of sense because you're loading all of this IP onto a pipe that has no flexibility. You have to go from a point A to point B with a lot of capacity, and that may not make a lot of sense. These days, that's changed. You can break out an individual wavelength and put it wherever you want it to be. And those wavelengths are no longer fixed. We have things like gridless, which means we can go to very high-speed wavelength bandwidth. Things like 400 gig and 1 terabit will be able to be supported on the same infrastructure. We have things like colorless and directionless and contentionless and all those other things with WDM, with ROADMs. Colorless essentially means it doesn't, well, let's start with directionless. Directionless means no matter where it comes in, it can go out anywhere, which is a huge deal again, because now if you want it to go east and suddenly you want to change and go west, you can do that. Colorless means it doesn't matter what color you come in, it can go out either way. And those are the two that have made the biggest impact, colorless and directionless. If you look at most of the projects that are going on these days, colorless and directionless is really the end-all be-all. But there's also this thing called contentionless, which means if I already have a red coming in and I want to put another red in going on a different direction, there's no restriction on that. And that's possible as well. It's a little bit more expensive, a little more complex, but you can do that. And what this has meant is that the WDM layer, the optical layer, has become just as flexible as the old TDM layer. And again, for those of us who've been in the business for a while, have studied this for a long time, this is magic. This is amazing stuff. If you think about how WDM started and how optical networks started, this was the holy grail, and we can now do that without even thinking about it. The hardware exists to make this very, very flexible. This is what has allowed us to really start talking about what can you now do with IP over optical, especially if you have intelligence across multiple layers. It's this flexible WDM capability. I will mention quickly flexible subrate packing, because if you look at the transport SDN definition in the standards bodies, and there are several that are working on it, they include everything down to the OTN layer. That's included as part of the transport SDN stack. And in the past, generally, when you talked about optical, you converted from one wavelength to another. You maybe have SONET SDH switching on there, not a whole lot of multi-layer capabilities. With OTN, those things are supposed to go away. And not to say anything bad about SONET SDH. SONET SDH was designed to do very, very well what it did. But it had some issues. First of all, it wasn't designed for data. It was designed around voice protocols. So when you got to things like 100 megabits per second, it didn't fit really well in something that was designed to go to 155. It also was somewhat over-engineered. If you spend any time with the SONET protocol, you know it had things in there like order wire, which allowed you to talk to somebody at the other end in case you didn't have a phone system. Well, we have cell phones now. That rarely comes up. It had reserved overhead bytes for future use. I think we can now safely say they will never be used. It had a lot of extra bandwidth sucking protocol stuff built into it that we really just don't need when we know networks are going to be based on data and on higher layer protocols that take care of a lot of that. OTN is designed to do that a lot easier. It's designed to handle TDM as well as SAN and WAN traffic very efficiently, packet very efficiently, and to be much more interoperable. And it has things like built-in forward error correction, which allows it to go over longer distances. So the world is moving, if any TDM at all is in the network, it's moving more and more towards OTN, which is a protocol that's very nicely designed for the idea of a flexible photonic layer as part of that stack that you can work with. The other part that I mentioned is the idea that network elements and networks themselves have become much smarter. These days, rather than having to have a lot of test equipment around, you can build test equipment type functionality into the elements themselves, which means your network now has an idea all the time of what its health is. You don't have to necessarily pull something out of equipment and go in and do a PRBS testing. You can have OSNR measurements going on all the time. That's measuring the health of your signals without actually having to break the signal. You can put in things like OTDR, which goes out and finds where the break is without having to come in and bring in a separate network element. You can look at performance monitoring. What all this gives you is the health of your network all the time before things fail. It allows networks to be much more intelligent, to be operated without having to have a huge staff constantly monitoring them. It takes a lot of the human error out of it. It allows you to find where the critical errors are before they actually occur, and to be able to look at all the different things that are happening and maybe filter out the things that aren't so important right now. The fact that networks are more intelligent and have all this capability built into them allows you to do all of the flexible things that we talk about. Because now you understand at a holistic level what's happening in the network, more than just what standard PM would have given you in the past. And because of that, we can now start talking about software-defined networks. SDN we could talk about for 30 minutes without getting into the optical at all. It started out really as something that was happening at the IP and Ethernet level. It is more and more migrating into the optical layer. But what it means just at a very, very high level is your network is now application aware. It understands what the applications are that are running over it. There's some controller or orchestrator high above that's able to not necessarily know all of the detailed capabilities of every piece of equipment out there, but it's able to understand what they are able to do at a high level and how to use those optimally for the applications that are running. It can do automated network responses. It can do things like network as a service, where someone comes in and asks for certain capabilities for a certain amount of time or on demand. There are applications doing this available today. The stuff that's happening in the optical is not quite as far along as what's happening in the packet layer, but there is some interesting stuff going on. I saw Sterling had written something about that recently. So go out and read about it. It's TAPI and some others that are working on that. This software definability, based on the flexible optical network that I just talked about, really gets us to where we are with IP and optical. Because we have the capability to now look at what's happening across the entire network, we're now able to orchestrate across those different layers, orchestrate IP and optical together, and get some really interesting applications going. And that's what this next section is. So those of you who were sitting back and said, yeah, I knew that stuff, this is where you can come back in. This is where we're talking about where is this going and what is this going to mean. So what's the future of IP over WDM? And the future is to take everything we just talked about, smart networks and flexible optics and flexible WDM and flexible SUBRATE packing, and run those through SDN and come out with new applications, improved operations, new network efficiencies, lower costs. To tie this back in a little bit to what Sterling was talking about with the different ways IP and optical work, one of the big debates is if we do have a controller in SDN that's able to see all this stuff in optical, would it make sense then to try to neuter that a little bit by putting the optics directly into some of the switching platforms and lose some of this capability? Because the switching platforms are never going to have this kind of flexibility built into them, because that eats up processing power that's necessary for the switching capabilities, and SDN is going there. So there are people who are looking at doing advanced IP over WDM, these new applications, and in many cases they pretty much require that those be somewhat separated, just because of the difference in these flexibilities. So if you look at some of the big guys who are very, very involved in SDN, most of the applications that are shown, those are separate, at least largely separate. For point-to-point applications, absolutely makes sense to continue to put those inside. But for these, a lot of times you'll see them separate. That's why that introduction leads into what we're talking about here. Well, to Sterling's point, we had the poll which said what's the #1 use for IP and optical integration, and that's multi-layer provisioning. And certainly that continues to be the #1 reason that people see this working. But it's not just understanding that we have nailed up pipes in the optical layer. We maybe even have some nailed up OTN layer, and how do I get my optical or my packet to work over that? It's more understanding what capabilities are out there in the network. I have a pool of optical resources. I have a pool maybe of OTN resources, and I need to get a packet service from one end to the other. How do I make that happen optimally? If you have an external multi-layer SDN controller up there that just sees these as pools of resources, and then there's subcontrollers or element managers or network managers underneath that can optimally figure that out. Now you're talking about the ability for a user or even the packet layer itself to say, I need to get from point A to point B, find me the best route that makes sense holistically across the network. The provisioning is coordinated all the way across, so the resources are allocated or even reallocated based on what's happening. Protection schemes can be coordinated, and that's always difficult to figure out. How do you make sure that those don't ring across different layers and that you have the optimal protection? This is really what we're talking about when we're talking about automated provisioning. There's been stuff out there forever which is point and click when you have everything else nailed up. What we're going to is something that has a flexible photonic layer, truly flexible, on top of a flexible packet layer, and now you can optimize for both of them, and that's where SDN is going to take us. That's probably the simplest application, and the one that everyone talks about when they look at that is, well, why would you want to do this? A lot of times it's because you want to minimize the use of router interfaces, because router interfaces are the most expensive interfaces on your network. Most of the time that's called router bypass. And in the past, router bypass has been something that everyone always talks about, unless you maybe work for a router company, as the ultimate place we want to get to. But it's always been relatively hard to coordinate. So rather than just say router bypass, we're saying intelligent router bypass, where it's finding a way to do this automatedly, where it understands what's going on with the router ports and can coordinate this across multi-layer networks. So at the fundamental layer, what router bypass means is if you have traffic at the wavelength layer that's consolidated, you're going through something like a packet optical system, keep it at the at the wavelength layer and pass it through. If you have traffic that can be consolidated at perhaps an OTN layer and never switched, keep it at the OTN layer and pass it through. If you have traffic that can be switched at layer 2 without ever having to be routed, and that can be MPLS or Ethernet or carrier Ethernet, whatever that has to be, keep it at that layer within your packet optical system perhaps and pass it through. Only when you get stuff that has to be routed can it be consolidated across all these layers and handed off to the router. And that's always been what we talk about as router bypass. These are the kind of diagrams that have been shown for years. But now we're talking about an SDN network where we have intelligence across the entire network, not just an element. That's where things get really interesting. Because now if you have a network and you have an Ethernet service coming in, perhaps the SDN controller can have some more intelligence there and look at what's happening at that first node and say, you know what, in this first node, I see a lot of traffic headed to node B, but not enough to fill up a wavelength. I'm going to pack it all into an OTN circuit, send it off in that direction. And what that means is when you get to that next node, it's a router bypass at the OTN layer. But then it can say, you know what's happening here? I see that there's a lot more traffic that's going from A to C here. I'm going to pack all these OTNs together into a wavelength. And that way when I get to the next element, I'll bypass at the wavelength layer and never even hit the OTN layer. This would be very complex to figure out, especially on an ongoing basis if people were having to do this manually through spreadsheets and management systems. But if you have an intelligent controller on top, now it can do this automatically for you and minimize your network resources. When you get to the other side, it understands I'm now handing off to the packet layer because it's multi-layer, it can see those as well, and go through a switch network as a packet IP Ethernet switching and routing. That's really, really simple way of showing what could be happening on a very, very complex network to minimize the use of those router ports and coordinate across multi-layer networks. That's the one everybody likes to talk about. But let's talk about some that are perhaps a little less traditional and more interesting. At least I think they're more interesting. One of them is intelligent network restoration. Generally, the way restoration has worked on networks is you have a spare port and you have an active port. When the active port fails, you switch to the spare port on both sides. The problem is on the other end, that active port is still fine, but you just put it out of service. It would be nice if there was a way to maximize the use of those different resources by intelligently understanding. And that's what had happened here with a flexible photonic layer and an SDN controller that can see multi-layer. You can imagine within this type of network, very, very simple here, the active port fails on a router. Well, now the SDN layer is able to say, well, I know there is a switch capability in there where I can just move that traffic from going the active port over to the spare port. Why don't I just move it to the spare port? Within the flexible photonic layer, I can change the wavelength, send it over the same ROADM. The active port on the other end never sees anything change. We've used half the amount of resources on the other side to do intelligent network restoration. And again, this is very, very simple, but you could imagine this going to a very large and more complex, perhaps mesh-based network, and significantly reducing the amount of spare capacity, hardware, and resources that you have to have on the network. That's where we're going to with IP over optical. As Sterling mentioned at the beginning, the flexible photonic layer by itself is nice, but when you combine it with the IP layer, that's when you start getting to see some really, really interesting applications. So instead of going on and on about this forever, I'll take this to the conclusion. I know we have another poll we want to get to. We want to make sure we have time for Q&A. But the conclusion is flexible photonic layer is mature at this point. The technologies are in place. It enhances the capabilities of IP layer, and now we're starting to talk about a very robust IP over WDM. It's not the old IP over glass point-to-point. Can you put optics into routers? We're doing some really, really interesting stuff here. And when you add SD into that, the future gets really exciting. So Sterling, I'll hand that back to you.
Yeah, excellent. Good tutorial and overview, Scott. So this is our final poll question. So Scott walked through a number of applications or use cases. So we're going to ask you what resonates the most in terms of the application. So what is the most compelling application for IP and optical integration? And there's the options as Scott had walked through them: automated bandwidth and services provisioning, better resource utilization and optimization, so the network optimization use case, multi-layer restoration as he had just walked through, or we have an option in here, something new, the best is yet to come. So one of the things we're starting to hear recently as this enablers come into place is that a lot of just what can be done hasn't even been fully worked through by the vendors and the service providers. So if you think there's more to come better than what's been talked about here, then you could click that one. Let's give a moment for that to come through. We can just move right into the Q&A here. Let's see. So, where to start? Yeah, so there is a question in here for flexible optics. You mentioned long-reach applications. The question is, how does the single carrier standards like PAM4 fit into this model? PAM4, I believe, is the one that Inphi is using for that Microsoft application, but maybe kind of talk through that and where you see that going.
Yeah, PAM4 is a really interesting idea, going to single carrier, getting the cost down, coming up with a standard that works over an optical network. It is limited to about 80 kilometers, doesn't really go beyond that. You do have to add things like dispersion management back in that you got away from when we went to coherent. But I think there are applications for it. I think that what you saw Microsoft doing with Inphi makes a lot of sense. When you have, what they said is for limited applications where they have two data centers in the same metro area that are 40 kilometers or so apart, they'll use these PAM4 optics directly in the routers and save having to put in anything else. But understand those are very limited. Those are point-to-point applications where they're doing dispersion management. I think that makes a lot of sense because if you're a Microsoft and you have a lot of that going on, it's a way to reduce the cost of your network. If you have a more complex network, if you're somebody even like a Google or a Facebook or Verizon, AT&T, France Telecom, British Telecom, I mean, those kind of guys, there are probably going to be fewer applications where that makes sense because it's nice to have a standard that works over a variety of distances. But for data center operators and for certain limited applications, PAM4 is a great idea. I look forward to seeing more of those kind of innovations. Yeah,
interesting. If you remember at OFC last year, and I think this is a topic that's going to really rekindle, I expect there'll be some updates this year at OFC, which is coming up. But last year, some of the optics vendors were pretty much put onto the defensive as soon as that Inphi Microsoft announcement was made. From ECI's perspective, how did it affect you, or how do you expect it to affect you? Was it something that caused a fair amount of fear within the ECI organization when that was announced?
No, fortunately, we're not publicly traded, so we didn't get to watch the stock yet that hit some of the other people.
That's true, right.
But there was a big question, which is actually one of the reasons we started talking about IP over optical again. There was some confusion in the market that IP over optical was only putting PAM4 optics into routers and getting rid of it. And they had not heard the other people talking there, the other suppliers and the other network operators saying there's a limited application for this. And even the vendors for Microsoft were saying this doesn't impact us all that much because it's only for a limited application. So, yeah, there was some education where we had to go out and start talking to people about it, which I think led to eventually this webinar. Yeah,
interesting. Yeah, and I'm sure this is going to heat up again in a couple of weeks because I'm actually very hopeful that they have an update on that, and I think it'll kindle a lot of discussion. So the poll question is out, the results, so hopefully you can see that. The one that came in on top in this poll, better resource utilization optimization, which I believe would map fairly close to your when you went through the router bypass application, followed quite a bit by the bandwidth provisioning. 12% think the best is yet to come, roughly. So any thoughts on that, Scott?
Yeah, I really hope that in 5 years we look back at this and say how quaint, because what great new applications have come out since then, and look how well they're being used. I really like to think of the network as a service being very much like the iPhone model, that once we get it open to the point where people can do things with it, we're going to come up with such really cool ideas. There's always the example of there's a carrier in Asia that opened up an API so that people could come in and connect into their points of presence through an API. And you could go into the API and you could figure out how much, for example, a 10 gig circuit costs a certain time of day. And what they found is that people started putting little polling things on there that would poll it all time during the day and figure out the best time to get 10 gig into certain locations, and it started selling that as a service. It was not in any way what was ever intended with that particular API, but it became a great way of other people making money off of their network that they didn't intend. they talked about this, I believe, at OFC last year, and they said, originally we thought about shutting it down, then we thought, why would we shut this down? This is a great idea. We just didn't think of it.
Right.
So I'm hoping that in the future something that we haven't thought of is going to be making all the difference.
Yeah, we will see, but it does need to prove in on the basics, and it does appear that it is. So once it's proved in, then you can do the interesting stuff, I think.
Absolutely.
There was a question came in from an operator on more of a clarification question, but I think in one of your early slides, because this question came in fairly early, you must have mentioned dynamic WDM, and just a clarification on examples of what is dynamic WDM in case you didn't cover that enough for this person.
Yeah, dynamic WDM just means the ability to do things with ROADMs on the fly as opposed to fixed WDM in the past. Fixed WDM in the past, you had, for example, optical add-drop multiplexers that were fixed to certain wavelengths, and you'd put those in line, you'd drop off at certain places. Whereas with dynamic, you can put a ROADM in there and decide in the future what wavelengths to drop, and you can change those through a software command. So no longer are you sending people out in the field to do rebalancing across a bunch of different amplifiers and perhaps changing out hardware if you change your optical layer. It's all dynamic at this point. And some of that can be automatic and some of that can be intentional.
Okay. Good. I think that clarifies. If not, they can re-ask here, and we'll put more detail. So an interesting question on OTN. You did talk about OTN, and a little bit of context behind this question, too, just from my own perspective is, so for data center interconnect applications, typically we have heard about there's IP and Ethernet, and then there's the WDM link. The question here is, why would I include an OTN layer for data center interconnect? Originally, I didn't think there was much appeal to this. I just recently learned, and I don't know if you've had this experience as well, but apparently in China, if you look at the web scale equivalents in China, they actually are doing an OTN, WDM OTN network for their data center interconnect. So I didn't realize their architectures were that different, but it is coming into play, maybe in other regions as well. But just so the question is, for all packet networks like DCI, why would I include an OTN layer? Maybe from your customer interactions, what you see.
That's a really good question. I wasn't aware of what was going on in China. I did have an opportunity to speak at an internet exchange group at one point, where essentially their distances are all relatively short because they're talking about within an exchange, and we talked about multi-layer integration and what they're doing with WDM and the flexibility, and all that was very exciting. But for them, when they asked, well, why would I use OTN, the answer probably is you wouldn't, because they are pure IP over a mesh network within a relatively small area, and each of those links is huge. When they talk about a 100 gig link, it's between 2 points that need 100 gig worth of bandwidth, so there's no reason to talk about a sub-wavelength for them in particular. So I think in some cases it has to be evaluated. It'd be interesting to see why in China in particular with their data center connect they're doing it. Obviously, OTN wrapping is certainly going to be used because that gets you forward error correction, which is a big part of it, gets you interoperability and all the other great things that go with that. The reason I would think OTN would make sense is as we start talking about going beyond 100 gig to 200 gig and to 400 gig and maybe to terabit, now it may be a little harder to fill up an entire pipe. Certainly if you're Google or Facebook or somebody like that, you could fill up a whole pipe relatively easily. But anybody else is going to have trouble perhaps filling up a pipe between two specific locations at that level. And if you still want to take advantage of the economies of moving to a wavelength at that speed, because it's always 200 gig is less than 2 times 100 gig, then you might have to start doing some things with OTN to give you that sub-wavelength granularity to be able to break those out and send them where they need to. That's my guess, but I haven't looked at what they're doing in China.
Yeah, no, I just recently became aware of this, so I need to dig in a bit more myself, but it was interesting. So at least from my own perspective, I'm not tossing out OTN anymore as an application. So, a question just came in, and we do have about 10 minutes. We have a couple questions in the queue, but we could take a couple more if you've got them. A question came in. Can you go into detail about Ethernet versus OC circuits in relation to this conversation? I don't know if that's clear to you as a question, Scott, and if you can address that.
I'm not sure exactly what OC is. If you're talking about optical carrier, perhaps?
That's my guess. For the person who's asked, if you can just punch in a clarification there, we'll take it. I think so. Does it? If it doesn't make enough sense as is, we'll hold off until we get some clarification.
Yeah, there's all sorts of different things when you start getting into giving an Ethernet circuit to somebody versus giving them an optical circuit, and all the different things that go beyond that. So I'm not sure exactly.
OC48 as an example. So yeah, Sonic.
Oh, gotcha. Okay. Why would you go to Ethernet versus Sonic?
Yeah.
Yeah. There's certainly a lot of reasons that people are going to a packet-based as opposed to a TDM-based. TDM has some nice features. So let me start out with that. And all the features that I'm talking about, by the way, also apply to OTN, which is why OTN is sort of taking over. TDM is dedicated point-to-point. If you want a dedicated point-to-point with very low latency and you know exactly where it is, deterministic and everything, that's a great way to do it. So OC or OTN or whatever it is, that's a great way to do it. There are ways of doing that now on packet, by the way. Things like MPLS-TP have been developed to do that as well. But the main reason that people have gone to Ethernet as opposed to something like a TDM generally is because the majority of the data that's being presented, especially if you're a data center operator or an enterprise, it's all data. It's all Ethernet anyway. So taking it from Ethernet, converting it over to TDM, and then converting it back doesn't necessarily make a lot of sense. If you keep it at the Ethernet layer, then you get the advantages of, for example, not having to offer a 622 megabit circuit, be able to offer a 100 megabit circuit or 150 or 175 or whatever you want to. You can also do statistical multiplexing where you have more capacity within your network. There's also some more flexibility with what you do with prioritizing different things. And as we talk about SDN and NFV, then you get some really nice applications on top of that where you can prioritize certain traffic or you can download a firewall in there and make that happen. There's some really, really cool stuff when you go to a packet layer. So the TDM stuff is not going to go away. Sonnet is probably going to start going away. In fact, if you look at the predictions for Sonnet, they've almost gone away already now. But things like OTN and MPLS-TP as an alternative to those will continue to be out there for those reasons, especially for things like low latency and deterministic ability.
Right.
That's the biggest reasons.
Well, I tell you, yeah, I mean, 10 years ago, thinking back, there wasn't a day that went by without me saying and writing OC 192 1,000 times, and yet I totally drew a blank when they put OC in there. So things move up, but you're right, there's forecast-wise, Sonnet, in SDH, there's barely anything in it, but that doesn't address the install base, which still is quite large because there's billions and billions spent over the years on that stuff. Maybe get two more questions in. An interesting one. On the controller, we didn't talk too much about the controllers. It's obviously a huge issue with SDN or topic. Who was building the multi-layer SDN or NFV controller that will make these architectures happen? A lot of interesting discussions around that particular topic. What are your views?
Yeah, that's really interesting. And this is one that I know, Sterling, you and I have talked about a lot in the past because the big guys want you to just use theirs. The Ciscos and Junipers and all those guys, Alcatel-Lucents. They want to come out with their own and then have everybody come begging on bended knee to them to get into their controller. Because even though everything's standardized, we know that there's always going to be something that has to be done. There are other alternatives, and there are people out there doing it that are all based on open source, and I really think that's where it's going. Things like ONOS and Open Daylight and the others. What we'll probably see, and what I think will happen, is we're going to have a very much a Linux model for these, where there is a open source community that builds the core, and then there are others that put wrappers on them and value added on top of them, very much like Red Hat or somebody like that would do. I think that's where we're going to go. You're going to see the Open Daylight and the ONOS cores happen, and then people like ECI, we've built something based on those as well, which allows us to monitor other people, so that if you have a primarily ECI network, but you have some other people in there, you could use ours. If you are somebody with the kind of resources that a Verizon or an AT&T or British Telecom or France Telecom or somebody like that, or Telecom Italia has, you might build your own based on that, or you might contract out to build something based on that. And as long as we are close on the standards and making sure that we get the APIs right, the integration efforts should be significantly less than it was in the past when we claimed we were going to be open. We never were. I really think that's where it's going to go. Is it's going to be based on open source, and there'll be a certain number of vendors building wrappers on top of it. Yeah,
it is interesting because you've got the domain controllers. Certainly for the optical layer, the controllers that are built for these particular optical systems, and then you have the higher layer controllers, which, as you said, some of the hardware suppliers are pushing quite heavily, and then you have independent software companies getting into controllers, and then you've got even large, just large like OSS, BSS type companies moving kind of down into that area. So there is a lot of convergence in our discussions with operators. There's a lot of questions and uncertainty around which way that would go. Why don't we close out with one last question, which to a degree relates to that topic. Multi-layer provisioning is in fact already available for single vendor. Question is, what extra does SDN add? Can you give your thoughts on that one in case we haven't kind of walked through that quite enough?
Yeah, I'll give a quote from that one, and I'm going to get the guy's name wrong, so I'm just going to say that the person in charge of doing this at level 3 and I were on a panel recently, and somebody on the panel presented their SDN solution, and his answer was, if you can't do multi-vendor, it's not SDN. One of the problems when SDN came out was that everybody suddenly claimed they could do SDN because they had built something proprietary in. The fundamental basis of SDN is it's got to be multi-vendor. It's got to be open. It has to be open source and be able to understand what's going on across the layers. If you just have a point and click that understands what's happening in a specific type of network element but doesn't really understand what are the requirements for the underlying services, that's not SDN. It is technically a software-defined network, but it's not SDN. That's where we've got to get. SDN is fundamentally multi-vendor. It's fundamentally application-aware, which is more than just a network operating system that has some multi-layer capabilities in it.
Yeah, I absolutely agree. Open is critical. If it's not an open multi-vendor, it's no different from in the context of IP and optical, it's no different from the 20-year history prior. So there's not really much different going on there. So for the audience, there should be a survey up in front of you. If you can take a moment to fill that out, we would definitely appreciate that. We are just about at the top of the hour, so we'll close out here. Thank you to everyone for tuning in today and for your questions, and thank you, Scott, and to ECI for sponsoring and speaking on this webinar. Thank you, everyone.
Thank you.